Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take a look at the 2D version or suite of function of our projectile problems that we looked at in an earlier video. This particular video, I'm going to go a little faster through the creation of each one of the functions because while I'll assume that you have watched the first video where I go a little bit more in depth, but essentially, in the version 1 of the problem, we are assuming that the scanf and printf are inside the function. In other words, that the information is collected from the user inside the function, whereas in version 2, we're assuming that the scanf resides outside the function, or the user, the information is collected parametrically through command line arguments. But the printing of the values is handled inside the function. In the third version, if you notice, we have a mix of ByVal and ByReference variables. The two ByValue variables, the v-init and the theta, are passed to the function, whereas the addresses of tfinal, yfinal, vyfinal, xfinal, and vxfinal are all passed by reference, which means that they can be updated inside the function. And then lastly, in version 4 of the Projectile 2D, we are actually going to be looking at arrays of values. In this case, parallel arrays where n dictates the number of elements in each one of the vectors or arrays. So without further ado, let's go ahead and get started. We're just going to jump right in. Make sure that you have pulled up the PowerPoint presentation with the two-dimensional motion problem, because we'll be pulling some of the equations from there. And then let's go take a look at our Projectile 2D version 1. Now, as I mentioned earlier, we're going to actually be collecting the information inside the function. So that means that we're going to have to go ahead and declare some temporary variables inside the function that we're going to ultimately use. The very least of which is going to be our v-init and our theta, because those are going to be the two absolute minimum input arguments that we're going to need to be able to do our calculations. The assumption, by the way, that we're making is that we are on level ground. So for instance, what you have here is that our y-init is going to be equal to 0, and also that our y-final is going to be equal to 0. And that simply, that just simplifies our problem. It's not necessary that we do this, but it just simplifies our problem, because we're not here to learn the physics necessarily. We're more here to learn how to program some sort of mathematical function or equation that someone else has given us. In addition to this, you also are going to need a vy-init variable. We can get away without having this. However, it does make things a lot easier, and you'll see why in just a little bit. And then we also need a vx-init variable. Once again, you'll see why in just a little bit. And then back to the position, then we also want to have a x-init, which once again we are going to assume is going to be 0, and then a x-final, which we are going to calculate. Technically speaking, this we also don't need to fix. We can actually have a x-init other than 0. So we're going to calculate the x-final from the utilizing the x-init, and as well as the we're going to utilize the v-initial and the theta. The last two variables that we need is going to be our t-init, which we are going to set to 0. Once again, likewise as before, we don't necessarily have to assume that. It just makes our calculations a little easier. And then our t-final, which we are going to calculate. Okay, so let's go ahead and initialize some of these values, not the least of which, as we said, was going to be our t init, which we were going to initialize to 0, our x init, which we were going to initialize to 0. We're going to calculate our x final, so we don't necessarily have to initialize it here. We also want to go ahead and initialize our y init, assuming that we are going to use it. And then in our y final is actually going to be equal to our y init. Note, this is technically extra. And I'm just going to point out here that we could actually handle this with a y delta. All right. Now, continuing on, we have our vy init, which we are going to calculate from our v init and our theta. Likewise, our vx init. So the first thing that we want to do is we want to go ahead and collect some information from the user. Now, we can get some guidance from our Projectile 1D version 1. And as a matter of fact, I encourage you just to go ahead and copy the instructions or the comment then to the user, and then come down and let's just go ahead and modify this just to speed this example up a little bit. So we want to enter in the v init instead of the y init. And then in addition to that, we also need to collect then the theta. So in this case, theta, and we use the address of theta. All right, from there, assuming that you've got valid values, you can actually calculate your vy init, and that is going to simply be equal to the v init times the sine of theta. In addition, you have the vx init, which is going to be equal to v init times the cosine of theta. The assumption here that theta is going to be provided in radians. Now, what you want to do is you want to jump over to your PowerPoint presentation to be able to get the equation for our t final. Fortunately, it's a little bit simpler than the last one. In this case, it's just going to be -2 times v0y divided by a0y or ay. So -2 times our vy init. And once again, I tend to use an abundance of parentheses here. So we're going to put parentheses around that, divided by our ay. Now, utilizing this, we can actually calculate not only the vx, excuse me, let me rephrase that. Not only can we calculate the t final, but we can also calculate the distance that the object travels, as well as the average velocity that the object has. All right, so the one that we're going to be interested in looking at is essentially going to be our x final. And our x final is just going to be equal to our x init plus our vx init times our t final plus our acceleration in the x direction. We're going to go ahead and put this in here, but you're going to quickly see that we aren't going to use this because it's going to be 1/2 times ax times t final squared. And we don't really need this unless we have some sort of acceleration in the x direction, but we will include it just in case for future reference, but our AX then is going to simply be equal to 0. Okay. All right, so let's go ahead and start building our table and see if we've missed any values that we wish to include. Once again, I encourage you to go up here to one of our earlier examples and go ahead and get some of the table structure here. We could, for instance, include the Y init, the Y final, the T init, the T final, VY init, and the VY final. Those are all things that we could technically calculate. As a matter of fact, I see one already that we've missed that we could include. So we have our VY init. We could also go ahead and calculate our VY final and our VX init, as well as our VX final. Let's put our table in here and then see what we can do or what all we can add to it. As I said, we have our Y init, our Y final, our T init, and our T final. Let's go ahead and move those two up to the top, the T init and the T final. We have our Y init, Y final, VY init, VY final. Why don't we go ahead and make a block copy of all of those values and then just simply convert them now to X. So X, 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 and so on. And then also X, X final, VX init, and VX final, which leaves us just a few more things to calculate. So we have our X final. So let's go ahead and calculate our VX final, which is just simply going to be equal to our VX init. Not all that interesting because, as we saw earlier, our AX is 0. So in this particular case, then it would just simply be AX, which is 0, times our T final. And for our VY init, so our VY final, we're going to also leverage the position equation and the velocity equations from the PowerPoint slide here. That is just going to be equal to our VY init plus, in this case, our AY times our T final. Additionally, you can go ahead and calculate our Y final. Although we assume that it's going to be equal to 0, we might as well verify that. And we utilize our Y init plus our VY init times our T final plus the 0.5 times our AY times our T final squared. Basically, it's just a repeat of the equations in the X direction. All right, I think we've got most of these. Just seeing if we've missed any variables in here that we've neglected to either calculate or initialize. Our T init we've initialized as 0. Our T final we calculated. Our Y init we initialized as 0. Our Y final we've calculated. VY init we calculated from V init and our theta. And our VY final we calculated. Our X init we initialized. Our X final we technically calculated. Our VX init we calculated from our V and our theta. And our VX final we also calculated. So about the only thing that I see that's missing here is our V init. And that is what's collected from the user. And then lastly then is going to be our theta. This is probably also where you want to put a friendly reminder of the units for your user, both in the question when they're prompted, but also here in the table, in the output table as well. All right, let's go ahead and save this. Let's go ahead and build it. And let's go up now to our main. And we've got a lot of leftovers from the last time we've done this. So if anything, what we want to do is we want to prevent the other things from running, and we want to focus now just simply on our Projectile 1D version 2. All right, so here's our Projectile 2D version 1. And all we need there is the parentheses followed by the semicolon. We aren't going to capture the return value or anything like that. But let's see what we get here now when we build this and when we try to run it. All right, so I'm going to CD to my documents folder, to my courses, to my EE233, to my projects, and then to my physics demo, my distribution, debug, and MinGW folder. All right, do a dir. There's our physics demo. And if I run it, we're prompted for our VNet. I'm just going to enter in 100, and then I'm going to enter in a value for theta. All right, and I want to get a reasonable value that I can sort of confirm that we're on the right track. And probably the most logical one would be the radian equivalent of 45 degrees, because ideally then our Vx init and our Vy init should be fairly close. So I'm going to enter in 0.785, just an approximation here, and hit enter. And you'll see that my T init is 0, my V init is 100, my theta 0.785, my T final, it took 4.39 seconds for the object to land. We would probably consider adding units here on the value. We can go back and tidy up some of those things later. Our Y init was 0, our Y final is 0. That means it's a reasonably good estimate there. Our Vy init is going to be 70.6825. Our Vy final, if you know your physics, that looks reasonable. It's basically coming back down at the same vertical velocity that it came up at. Our X init 0. Our X final is 310. In this particular case, we're assuming that it is in feet, so it's going to be 310.5589 feet. Our Vx init 70.73, which is pretty close, although not exactly the same as our Vy init. But more importantly, our Vx final matches our Vx init because there's no acceleration in the x direction. Now, we'll leave some of the cleanup to another video, including adding units and also some of the logic that we're going to do in the main. But let's get back to the next part, next function in the suite, and that is the Projectile 2D version 2. In which case, what we're going to do is we're going to leverage a little bit of what we've done in our 2D version 1. But the difference being is that the V init and the theta are going to be provided for us by virtue of the function signature. Now, we would want to do some error checking, make sure, for instance, the velocity is not negative, assuming if we're talking about at least the projectile scenario that we're talking about, where we're shooting, say, a cannon on open ground or something along those lines. And we might also want to consider doing some error checking for the values of theta to keep it, for instance, between 0 and pi/2. Neither of those are completely essential because the physics formulas will work. But essentially, these values right here are going to be provided by virtue of our function signature. So what we're going to do to speed this up is we are going to come along here. We're going to go ahead and copy the whole block of code. And essentially what we're going to do is just remove certain pieces. And so particularly, we're going to remove the portion that captures the v-init and the theta. All right, so I'm going to go ahead and do a Control X there. But what I am going to do is I'm not going to throw that completely away. I'm actually going to come along and I'm just going to launch Notepad and I'm going to paste this because we're going to use it in just a little while. And the other thing that we want to do is we want to come along and we want to eliminate this redundancy here. So there's our v-init and there's our theta. We don't need to redeclare those inside of our function. So we want to go ahead and get rid of those. And we're going to come over here to our Notepad and we're going to go ahead and add those. All right, so basically think of this just as a little more persistent clipboard. All right, aside from that, essentially all we have to do now is provide those values by virtue of passing them to the Projectile 2D version 2, which means we are once again going back up to main. I'll tell you what, we'll maybe collapse some of the other ones so that we don't have to do quite as much scrolling here. But to start off with, what I want to do is I want to simply say Projectile 2D version 2. And I want to pass those exact same values that I did earlier to test this out. So 100.0 and the 0.785, just to see if this works the exact same way. All right, so I'm basically hard coding these. Control S to save it, build it. And then once we verify that we don't have any errors, we come back here to the command line, clear the command line, and rerun our physics demo, and we get the exact same values again. So basically, whether we hard code the values and call the function or use a scanf and a printf doesn't really matter. And particularly, it doesn't really matter where you collect the information. So then the third option here, much like in the earlier example, is that we could simply collect the information using this printf and scanf outside, in other words, in our main. And then the only thing that we would need to do is we need to provide these variables, these v-init and the theta. So the reason we used our clipboard here was just so that we wouldn't have to retype all this. But we can come up here now, and in addition to these values, we can also specify a v-init and a theta. So again, I build it. Let's make sure that I have commented out everything I intended to. Actually, I commented out perhaps a little too much. So let's go ahead and add this back in, Projectile 2D version 2. And we want to pass to it a v-init and a theta. And if we build it, come back over here to our command line, hit the up arrow once again and run it. We're prompted, put in 100. Enter the theta, 0.785, and sure enough, we get the same table. So basically, we could hard code it or we can enter in the values interactively. Which then brings us to our third example here, and that is, what if we want to pass them by the command line? Well, we already saw this last time when we were looking at our version 1 of the, or version 2 of our 1D problem, in that instead of simply prompting the user over and over again using the printfs and the scanfs, we could simply just check the number of arguments that were passed to the command line. And then based on the number of arguments, we would choose which function was to be run. And in this case, we know that with the 1D problem, if you provided 2 arguments, at least it was implied there that you wanted to run one of the 1D problems. Okay, it doesn't matter which one right now. We're actually going to get to that in another video. But what I want to do now is I want to go down here in line with my if statement here. I want to come down here to where my if statement closes. And I want to follow this up now with an else if. And else if my argc was equal to 3. Well, why would it be equal to 3? Well, it would be the name of the executable followed by 2 values. One would be my v-init, and the second one would be my theta. And to handle that, we're going to do the same trick that we did earlier with this A to F function that allows for you to convert from a string into a numeric type. But this time around, we're going to do it with 2 of the arguments. And so our v-init is going to come from the A to F of our arg v square brackets 1. Remember that square brackets 0 is the name of the executable. And then our theta comes from our arg v square brackets 2. And just that quickly, we have converted our interactive projectile 2D version 2 into a parametric one, where we are simply checking the number of command line arguments. To see how this works, I'm going to build it. I'll tell you what, to make this just a little more responsive here to us, I'm going to put an else in. In other words, it's assuming that it didn't get enough information. And all I'm going to do here is printf note or warning unhandled number of arguments. All right, so at least now we can check to see if our logic, our very simple logic here with our argc is working. And to do that, we just run our physics demo with no switches, no arguments, no nothing, just hit enter, and it comes back with the warning that says unhandled number of arguments. Now, we already know what's going to happen if we put a single argument in, and that's for the earlier video. But let's follow this up with 2 arguments. So there's our 100 and our 0.785. And if we hit enter, sure enough, it calls the function or projectile 2D version 2. Why? Well, because the number of arguments equals to 3. By the way, note, if we put something else after this, it's also going to return back unhandled number of arguments because it was looking for 2 or 3, not 4. All right, so continuing on, let's come back here, and now let's focus on the projectile 2D, but this time let's look at our version 3. And what we're going to do is we're going to see how much of the code can we borrow and manipulate from the previous example. Notice how many variables are passed, either by val or by reference. And notice then that we don't have to re-declare those. Okay, rather what we're going to do is we're simply going to leverage them. Note also that since these are by reference, we can do some of the formality, in other words, some of the printing outside the function, because essentially our t final, our y final, our vy final, our x final, and our vx final are all updated inside the function to be used outside the function. So that being said, essentially what happens is we significantly reduce the number of variables that are needed. As a matter of fact, what we're going to do is we're just going to, once again, we're going to copy, and we're going to take a look at where the redundancy is. All right, and if you notice here, we have a v-init. Well, we've already taken care of that in the earlier example. We have a t final. If you come down here, we don't need this one. We have a vy final. That's here. We don't actually need that. We have a x final. Don't need that. And we have a vx x final. All right, and I think I've skipped over one on accident. There's our y final. So actually we have 1, 2, 3, 4, 5 variables that we can avoid having to redeclare. We also want to be careful not to initialize any of these. Okay, in other words, be careful. We don't want to initialize particularly any of our ByVal variables, because essentially those were meant to be passed as input arguments that we would use, namely the v init and the theta. Now, the only other minor modification that we need to make is we need to use the indirection operator, okay, to specify then our t final, our x final, our vx final, our y final, and our vy final. And in this case, if you notice, we have a couple of our equations also utilize a variable that is passed by reference, in which case we also need to use it there. So in other words, anywhere you see your t final, you're going to want to put the indirection operator. All right, I think we've got all of them. Let's see anywhere else. All right, let's go ahead and build this. Let's see if we've got any issues so far before we go any further. All right. Let's see what error we've got here. Ah, yes, the way we've declared this. So our y final, or not declared the way we've tried to initialize it. So there we go. That should then make that one happy. All right, good. So now let's go about trying to figure out how we're going to handle the table, because we wouldn't logically print the table out inside this function. Instead, what we would want to do is we would want to leave all the presentation to the calling function. So this entire table right here can then be moved up into our main. So we're going to come up here into our main. And now inside the branch that is looking for argc equals to 3, translation, our 2D problems, whereas the earlier ones were the 1D problems, we can simply copy and paste the entire table. And the only thing that we've got to decide then is how are we going to handle some of these initial values. Now, we could use variables here, or we could do the same approach that we did up here, where we simply just hard-coded the initial values in. Either is perfectly fine, just as long as you're aware that you could technically use this. You could expand this out, be able to use use this elsewhere. And then our vy init and our vx init, we've got a little bit of a dilemma there, because we did not pass those by reference. So we technically don't benefit from getting those values using that function. So arguably what we would want to do is we'd want to rewrite that function signature to also include a vy init and a vx init in the calculation. All right, but we'll come back to that in just a second. The x final, actually in this particular case, our x final is going to just need to be a variable. So let's go ahead and include them in here. So we already have a v init, a t final, a y final, a vy final. So we also need to have a x final and a vx final. And then let's see if we're missing any other variables right here. So our vx init and our vy init. Now, in lieu of the fact that we don't pass those variables by reference, at least for this example, what we're going to do is we're simply going to replace this with the same equations that we used inside the function. So in this case, it's going to be v init. For the vy init, it's going to be v init times our sine of theta. And for the vx init, it's going to just simply be v init times cosine of theta. Hopefully you can see that we would probably in the future want to consider adding those to our function signature. That seems like a reasonable addition. All right, once again, extra set of parentheses, and assuming then that we've got all of our values passed, or the correct number of values passed, the only thing left to do then is to initialize any value that would not have been passed to the user, or passed by the user through the command line. And so those would be things like our y init, which was going to be equal to 0. And our t init's not printed here. I think we've got everything else. So what we want to do now is we want to call not our Projectile 2D version 2. What we want to do now is we want to call our Projectile 2D version 3. And we want to pass to it our v init, our theta, our t final, but more importantly, we want to pass it by address. So we use the ampersand in front. We also want to pass to it. So occasionally you will lose your function signature, in which case the simplest thing to do is just to come down here in netbeans, find your function that you're interested in. So it's the v init theta, the address of t final, the address of y final, and vy final. So it's going to be ampersand y final, ampersand vy final. And then if you take a look down here, you continue to scroll here where my mouse is, you'll see the address of x final, followed by the address of vx final. All right, I think we've got everything. I don't immediately see anything we're missing, although we might come across something. Let's go ahead and build it. All right, let's come back here to our command window. And this time around, we have to make sure to provide it with 2 arguments. In this case, there's my 100 and my 0.785. That's 2 arguments for a total arg count of 3. And then if we hit enter, once again, you'll see our nice little table with our t init of 0, our v init of 100, our theta of 0.785, our t final of 4.39, and our y init of 0, y final 0, and so on all the way through. So it looks pretty reasonable. So unless we've made some mistake that you don't immediately see, I think it's about time for us to look at our 4th version of this. And so the 4th version differs from the other ones by virtue of the fact that it includes a vector or an array of values. So this last one now doesn't calculate a single value, but rather what it does is it uses arrays that are passed by reference to calculate multiple values. Now, what I encourage you to do is briefly take a look at the 1D version 4 to see what the differences were. Most notably, you will have to have a few temporary variables that are not included in your function signature. Most importantly, you'll notice that we have a t init, okay, as well as a t final. But then once we get the t final, essentially we use the t init and the t final to calculate a t delta. Now, using that T delta, remember we then created a parallel array, or rather utilized the parallel arrays using the n for the number of elements in the array. And then we created, in this case, 3 parallel arrays. The main difference in this example down here is that instead of 3 parallel arrays that are going to be updated, we have 2 input arguments that are passed by val, and then 1, 2, 3, 4, 5 variables that are passed by ref, followed by the n, which simply controls then how many elements are in the vectors or in the arrays. So that being said, let's get started on this one. And there's probably not enough duplication between this one and the last one to justify copying blindly down. So let's go ahead and do this one manually, I guess you could say. So we'll start off. We know that we're going to need to get a T final. And just for completion's sake, we're going to go ahead and have a T init as well, even though we may not technically use it. We also are going to have a Y init, and we're also going to have a X init. Likewise, we're going to need to have a VX init, a VY init. We have our theta. We are provided with a time vector, a Y time, and so on. So about then the only other thing that we will need is going to be a T delta and a index variable. We might have missed something, but we will add it as we come across it. All right, so the first step that we want to do is we want to calculate our T final. And as we said before, our T final is a little simpler than the previous one. It's going to be -2 times our VY init. And that is going to be divided then by our AY. That leads us to question, where did we get our VY init from? Our VY init is going to be equal to V init times our sine of theta. And since we're at it, we might as well go ahead and calculate our Vx init, which is going to just simply be V init times our cosine of theta. And then the other thing that we missed actually in the earlier example is the fact that you could add then our T init onto this to be able to get the shift essentially in our starting time. All right, so just keep that in mind though. For this example, we're going to have a T init equal to 0, and for most of these, then that's going to be the assumption that is going to be made. All right, so we're going to have a T init equal to 0, an X init equal to 0, and a Y init equal to 0. All it does is it simplifies the equations. Okay. Now, once we've got our T final, we want to move on to calculating our T delta. And our T delta is going to be equal to our T final minus our T initial divided by n minus 1. And that's the reason it's n minus 1 is because n represents the number of data points, whereas the delta represents the time or the distance between the data points. In this case, it's time between data points. And so therefore, you're going to have one less segment than data points. So therefore, you want to divide by n minus 1. From there, it's very similar to the previous example. We start off with a for loop where we set the initial value to 0. We want to continue while index is less than n, which n is the max number of elements, and then index plus plus. And from there, we just build the 5 parallel arrays, starting with the time vector or the time array. So time square brackets index is just simply going to be equal to our t init plus whatever the index is times our t delta. So for the first iteration, when index is equal to 0, it's going to be 0 times t delta added to the t init. Now, continuing on with this then, our x delta, or x delta, not sorry, our x vector rather. Let's do it in the order that we have them up here. We actually did y as a function of time next. So our y as a function of time, square brackets index, is going to be equal to our y init plus our vy init times our current time, or time square brackets index, because it's the value of the time at that particular instance, plus then 0.5 times ay times the power function of our time square brackets index to the power of 2. Next one we're going to need is going to be our v underscore y underscore time index is going to be equal to our vy init plus the a underscore y times our time value. Very, very similar set of equations now for the x direction. So this is the y direction. So for the x direction, very similar. It's going to be x underscore time square brackets index is going to be equal to x underscore init plus our v underscore x underscore init times time square brackets index plus the 0.5 times our a underscore x, which we said was going to be equal to 0. We'll just stub that in with a temporary variable top if we ever need to use that in the future. And then our at squared is essentially going to be time squared using the power function. Last one then is going to be Vx time square brackets index is going to be equal to Vx init plus then 0.5, or not 0.5, sorry, a underscore x times time square brackets index. Once again, I'm going to come up here. I'll create a temporary variable. It's going to be a double a underscore x, and we are going to initialize it then as 0. All right, let's go ahead and save this. Let's build it. See if we've got any typos, any bugs that we need to handle. If not, let's go back up to main and let's figure out how in the world we're actually going to display all of this information that we have. We can probably leverage one of our existing tables and maybe just simply add a little more information. And so in this particular case here, what we want to do is let's call our Projectile 2D version 4. And to that, we want to pass our v init, our theta, and then we want to start passing then instead of individual values by reference, we want to pass our time vector, our y as a function of time, and our vy as a function of time, as well as our x as a function of time and our vx as a function of time. Now, note we've got to go create some of these variables, particularly the x time and the vx time. We've already created the y time and the vy time from our earlier example. So if anything, all we have to do then is add a couple of more vectors here. So we're going to have a double x underscore time. I'm going to hard code the 11 for right now. Double of a v underscore x underscore time of 11. And we already have our time vector here. We already have an n. And we should have somewhere around here, I believe we've already created a index variable. Okay, so we're going to leverage that index variable. And then what we're going to do down here is we're going to use this table. We're going to make a copy of it real quick. Tell you what, I'm going to move this down just a little bit because I don't want to mess up anything we've done so far. But instead, what I want to do is I'm going to leverage this one. I'm going to comment out this and make a copy of it, see how much of it we can reuse. Except, like in the previous example, we aren't going to have some of these. We have our v init and our theta, but our t final is essentially going to be our time vector, and it's specifically going to be the 11th value in our time vector. Our y init, 0. Our y final is going to be the last value in our y time vector. We can leave our vy init alone because, once again, that hasn't really changed. Our vy final is actually going to be the 11th element in our vy time vector. Our x final is going to be the x underscore time, the 11th value there. Our vx init still going to be calculated from v init and cosine theta. That doesn't change, but our vx final is going to be v underscore x underscore time and then 11. So that gets us the core of our values, or the initial values. Now what we want to do is we want to present a nice little table here using a for loop. So we say for index equals to 0, index less than, I'm going to go ahead and put in my n here because I have an n specified above as 11. You can hard code 11 here, but just remember that you've done so. And then index plus plus. And then once again, we get to play a little bit of a guessing game, trying to make our values look good. So outside of this for loop, I'm going to print f. I'm going to put maybe a index tabbed over a times square brackets index tabbed over again, x as a function of time, square brackets index. Tell you what, just to make this a little bit shorter, how about if we just drop the index part? So there we go. And then we have v underscore x underscore time, y underscore time, and then v underscore y underscore time. Guaranteed that we aren't going to get this right the first time. Let me show you a little bit of a sneaky way to go about doing this. I always make a copy of this inside the for loop and then delete it later. What this does is it gives me a rough estimation of where my numbers should be. So I have a %d for the index, a %d 8.4F for the time. We're going to utilize this multiple times here, so I'm just going to copy and paste this. And then once again, we've got quite a few placeholders here. So the first one is just going to be the index. The second one is going to be times square brackets index. The third one is going to be, I'm going to go ahead and continue on to the next line here. Third one is going to be x underscore time index. And then fourth one, v underscore x underscore time index, y underscore time index, and then lastly v underscore y underscore time index. I think we've got them all. Let's see here. Let's see if we've got any mistakes. Probably worth going ahead and commenting out our helper line there, and then go ahead and make a copy for your table of that border. Let's go ahead and save it. Let's build it. Hopefully we don't have any mistakes. Let's see here. We did have one. Too few arguments. All right, let's see what we goofed here. So we have vianet theta time. Oh, yes, yes, our most important one there, the number of elements in our vector. All right. Might even want to consider including that in on your table for your input arguments. All right. Simple mistake there. Let's go ahead and clear our command line. Let's go ahead and run this one more time. We didn't quite get our borders nice. Let's go back and clean this one up just a little bit. Looks like I need to shift the X time just slightly, maybe the space. Let's give it another quick shot here. Come in here, we'll put another new line. All right, and then we'll put another border line in there, and how about a space there and a tab there? And that should get us pretty close. Build it one more time. Once again, this is just down to the aesthetics and playing around with it a little bit till you're happy with it. All right, we're getting there. Just takes a little more effort. Maybe make our borders a little longer. Tab over the Y time, and so on. So we'll go ahead and tab this over. We'll just double all of our borders for this one, including the ones on our main table up here. And once again, not perfect, but it's getting there. And if you take a look now, we have our index of 0, we have time 0, x time is 0, vx time is the velocity in the x direction at any given time. Notice it's constant. Why is it constant? Well, because there's no acceleration in the x direction. Our y is a function of time, and our vy as a function of time. And from our previous examples, we know that it's going to be 4.3902 for the time at the 11th element, or t final. So all in all, it looks about right. And I think we're about done with this part of the example. So as always, if you've got any questions or any suggestions, don't hesitate to email me. Thank you very much.